And here we are in Intermediate Algebra's last section of Chapter 3. This is 3.6, where we're going to talk about systems of equations in 3 variables. There are some different scenarios that you can run into when you're working with a system of 3 equations in 3 variables, and I'm not prepared with visual aids, so I'm looking around frantically to see what I can use. Here we go. Those and one of those. All right, I've got some really fancy visual aids here. Just below me there, you can see one example of a system of 3 equations with 3 variables. And what you need to know conceptually is that one of those equations, just one of them, if you were to graph it in 3-dimensional space, you're going to get what's called a plane. And a plane, without the string, see if I can get that string under control. There you go. A plane is a flat surface. And the string is distracting me. Here you go. A plane is a flat surface. And this flat surface could be sort of flat like this, or it could be tilted like this, or it could be pitched like this. Could be oriented any number of different ways. But just be aware that one of those equations makes a flat surface, a plane. Now, if you have 2 of those, then what you end up with is, well, you end up with 2 planes. And what are the chances of 2 planes colliding in midair? Well, in this case, the chances are pretty good because these planes are infinitely large. They're very expansive. So when we have 2 planes, you have only a couple of possibilities. One possibility is that these 2 planes are just sort of hovering above and below each other, and they're sort of, so to speak, traveling in the same direction, or they're both pitched the same amount and in the same direction, or rotated the same, so that they never end up touching each other. The other possibility is that these 2 planes are going to come together and they're going to meet. And if you'll notice, they kind of meet in a straight line. This is so, it's a little bit embarrassing. I'm using a folder I've worked it over so much that it's actually cracked open on one side, and the other thing I'm holding is a crumply ream of paper. But anyway, you can see that these 2 surfaces meet in what looks like a line. How many points are there on a line? Infinitely many. So when you've got 2 planes that meet in 3-dimensional space, how many solutions are there? How many points of intersection are there? Infinitely many. Unless those 2 planes don't meet at all in 3-dimensional space, in which case you have no solution. Now's when it gets dicey because I only have 2 hands, and I really need to be working on a system that has 3 equations, which means I need 3 planes. You should look in your textbook because there is undoubtedly in this section going to be an illustration. Let me just pause this and see if I can find one for you. Okay, I found one. And I have to give thanks to courses.lumenlearning.com. I just jumped onto Google and found this illustration. I wasn't able to pull up the ebook for my course because on an iPad, my ebook doesn't like to open. So check these out. I should really have taken a screenshot of these so I could draw on top of them. But on the left, option A, you're seeing 3 flat surfaces, 3 planes, where there isn't a place where all 3 of them actually meet. At the top there, 2 of the planes are meeting. In the bottom left, 2 different planes are meeting. In the bottom right, 2 different ones, and so on. So there aren't any places where you've got 3 points, or 3 planes are all meeting together. In the middle, there are 2 horizontal planes. One of them is kind of teal colored, one of them is a bit darker blue. Those two are parallel to each other, so they never touch. And then there's this orange one that's kind of slicing vertically through them. And then on the right, option C is obviously a stack of three planes where none of those three meet at all ever. Let's see. Let me pause again for a moment and see if I can find another good example of an illustration of where they do actually all meet. Okay, this thing's a little freaky looking, but it works. Right in the middle, you can see it. It's right in the middle of the image where the yellow and the green and the weird salmon color all seem to come together. It's literally right in the middle of the screen there. It's almost like there's a little white dot right. Oh, I can zoom in. It's like there's a star being born right there or something. I don't know. Anyway, that is the one and only point that all three of these planes have in common. So this system of three equations in three variables has one unique solution. And that solution is going to be expressed as not an ordered pair, but an ordered triple. Three coordinates, x, y, z. All right, so this is one of the scenarios where we do actually have a solution, and that's one unique solution for a system of three equations in three variables. Now, another scenario where you have a solution, but you have infinitely many solutions is something like this. These three planes are all kind of coming together and sharing not just a point in three-dimensional space, but a line of infinitely many points. And that black sort of double-ended arrow there is where all three of those planes come together. Imagine going to the beach and you've got the water and the sand or the soil if you're at a lake and the air. All three of those mediums or media are meeting together and they make up a thing called the shore. And is the shore just one point? Of course not. You walk along the shore. It's this long thing. It's not usually a perfectly straight line, but in this case it is. So if you would like to use that as an analogy to see how these three things can come together to create a line which contains infinitely many points, that might be a good one to use. How are you going to express an answer to a system of three equations in three variables that has infinitely many solutions in the shape of a line that's in three-dimensional space? I'll tell you it's a little bit tricky, but I'm going to show you how to do it. So let's keep moving. Let me get back over to some example problems. All right, here we are. I got to settle in. It's time to do some work. If I can find my pencil. There it is. We have 8% battery left, so let's see what we can do. This first system has one solution. It's consistent, and it's dependent, which is interesting because dependent usually means that, like in the case of two lines, that those two lines are the same line. They kind of depend on each other. But the language changes depending on the scenario. So let's start exploring this one. And you might recall from a couple of videos ago, a couple of sections ago, I mentioned that we're going to need to know how to process or work with pairs of equations using the addition method, or sometimes called the elimination method. And that's what we're going to do right away here. I'm going to label my equations 1, 2, and 3. And I'm going to eliminate one of my variables. Which variable should I eliminate? I try to choose a variable that has a coefficient of 1. And in this case, in equation number 1, x and z are both an option. In equation number 2, the variable y has a coefficient of -1. That would be good enough. But for this first one, I'm going to use the x variable. I'm going to eliminate all of my x terms. So I'm going to take equation number 1. I'm going to do this work over here. Let's take equation number 1 and multiply it by -3. That gives me -3x minus 6y minus 3z. Don't forget to multiply the right-hand side by -3 also. And that's equation 1 times -3. Below that, I'm going to write equation number 2. Just kind of copy and paste it over there. 3x minus y plus 2z equals 13. And that's equation 2. And then I'm going to add these together. And you'll notice that the x terms cancel out. You can draw a line through them if you want to. I think that's sometimes a little sloppy. Or maybe you could just circle them. Or, since you know they turn into a 0, just don't write them anymore. In the next column, negative 6y's plus 1 negative y makes negative 7y's. And adding the z's together leaves us with a negative z. And to the right of the equal sign, we have 10. Notice that this equation is missing the x term. I'm going to call this equation 4. And we just finished using equations 1 and 2 to create equation 4. I'm going to go back to the original problem, the original system of equations, and I'm going to grab a different pair of equations. I'm going to use equations 1 and 3 this time. And I'm using 1 and 3 because my goal is the same. I'm still going to try to eliminate the x term again. But we already eliminated the x term. I know, we're going to eliminate it again. As you create equation 4, which we've already created, and equation 5, which we're about to create, do you always eliminate the same variable from both of those equations? Yes. Every time? Yes. All right, so let's try to eliminate x one more time. This time I'm going to take equation number 1 and multiply it by negative 2. So I would skip a line in here. And then times negative 2, right? So that's negative 2x minus 4y minus 2z equals negative 2. That's equation 1 times negative 2. Below that, I'm going to write equation 3. That's 3x's and a positive 3y and a minus z equals negative 8. That's equation 3. And then we'll add those. And we get x minus, oh wait, something's wrong. My eye went to the wrong place. I was going too fast. This is supposed to say 2x right here. 3y minus z minus 8. Okay, everything else was good. Just make that one little fix. We're going to change this to a 2x. I knew that was wrong because they were supposed to cancel out the x terms. And now they do. And we do have a negative y remaining. And minus 3z. And a negative 10. And we're going to call this equation 5. Equations 4 and 5 now make up their own little system of equations. And you've already solved small systems of equations like that, linear equations in 2 variables. So we're going to solve this little system. And I'm going to continue using this addition method. So I need my terms to cancel out. And the smaller value that I can use, I could take equation number 5 and multiply it by negative 7 so that this turns into a positive 7y, so that will cancel out with my negative 7y from equation 4. But I don't really want to multiply by negative 7. I'd rather take equation number 4 and multiply it by negative 3 so that turns into a positive 3z, which will cancel out with my negative 3z when I add it to equation 5. So let's do that. I'll skip a line in here so you've got space between each little collection of arithmetic and combinations of equations. I said I was going to take equation number 4 and multiply it by negative 3. So that makes 21y plus 3z equals negative 30. And then we'll use equation 5 as it is. That's a negative y minus 3z equals negative 10. And then I'm going to add those together. As a result, the z terms are going to cancel out, and we're left with 20y equaling negative 40 on the right-hand side. And it's at this point where I start to feel like things are probably going correctly because I'm going to solve for y by dividing both sides of my equation by 20, and I'm going to get a nice number. I'll put a little note over here that I'm dividing by 20, and I get y equals -2. Beautiful. I'm going to circle that. I'm not putting a box around it yet because it's not my final answer, but it's part of my final answer. In order to find the next part of my solution, the next variable, I'm going to take this y value and I'm going to plug it back into either equation 4 or 5. Do we always plug that first variable that we figure out back into equation 4 or 5? Yes, every time. And when I do that, I'll be able to solve for z. Do I want to plug this into equation 4 or 5? I would say that since this says -3z and this says -1z, I tend to want to plug it into equation 4. But again, it won't matter. Let's put a little note that says substitute or plug into 4 or 5 and solve for z. All right, equation 4 is right at the top of the screen, so that says -7 times my new y value of -2 minus z is equal to 10. We used equation 4, so I'm still writing down equation 4 next to it, and then we'll solve for z. So this is equal to 14 right here, so I'm going to subtract 14 from both sides, minus 14, which leaves us with -z equaling -4, and then multiply both sides by -1, and you've got a z value of +4. We've got 2 out of 3 of our variable values. Now I'm going to take both of these values at the same time together, and I'm going to plug them into one of my original 3 equations. Let's go back over and look at our original 3 equations. Now we've got a y value and a z value, so we're solving for x, and my first equation has a 1x in it. So that's going to be very convenient to use as we solve for x. Let's plug those in there. Trying to keep all of this on the screen at the same time. Hide me for a moment. Sub z and y into 1, 2, or 3. And we're going to go into 1. So this now says x, which we don't know yet, plus 2 times our y value of -2 plus our z value of 4 is equal to 1. And that's equation 1. We'll do a little arithmetic. Oh, look at that. We have got a -4 here and a +4 here. Those will cancel each other out, leaving us with x equals 1. Perfect. We've got all 3 of our values, so we can present our solution. Our solution is an ordered triple, x, y, z. And in this problem, that's equal to 1, -2, 4. It's a single point in 3-dimensional space. It's kind of impressive that we can find that. I think it is anyway. Let's glance over into our left-hand column where we have all of these original systems of equations. As I mentioned, there are some other scenarios. One scenario was where we have one individual unique solution, a single point in 3-dimensional space. We just found one of those. The other possibility is that we have an inconsistent system where there's no solution. You'll know that you've encountered an inconsistent system if you work through the process and at some point arrive at a statement that says something like 0 equals 3. You should include that in your notes. It looks very similar to when you have no solution when you're working a system of 2 equations, You'll just happen to, at this point, be working with 3 equations in 3 variables, but you'll still run into this weird anomalous thing where you have 0 equals 3. When is that true? Never. Therefore, no solution. So I'm not going to go through the motions of working that one out. Yeah, that one doesn't really play out super obviously anyway. And then the other possibility is where I showed you that black double arrowed line that indicated infinitely many points on a line. We talked about the shore where the sand and the sea and the air meet. I would like to work through one of those, and I'm hoping my iPad battery holds out. This second system says we've got infinitely many solutions, so in order to keep that on the screen, I'm going to go ahead and just erase all the rest of this. I guess you don't have to watch me doing that. I can pause. Be right back. All right, I'm down to 5% battery. Let's see if we can do this. We're not working the inconsistent system with no solution, so I'm going to erase that. And we're going to work the system that's above it that says infinitely many solutions. Let's number our equations, 1 and 2 and 3. Let's pick a variable to eliminate. How about our y variable this time? Doubling something in my mind. Okay, I was looking to see if there was a quick and obvious way that we could maybe narrow this down to discover that we have infinitely many solutions. Let me just see for one more moment if anything jumps out at me. Not seeing it. 3 of those. Yeah, that might do it. 24, 30. Right. So it's a little unorthodox, but it works. I happen to spot it. When we were working with systems of 2 equations in 2 variables, remember that if we came to a point in the solution process where we had x plus 13 equals x plus 13, or just maybe -2 equals -2, or 0 equals 0, when is that true? All the time, right? 5 equals 5 all day. So that was an indicator to us that we had infinitely many solutions. In that case, it meant that the 2 equations were the same. In this case, we're going to run into a similar scenario. And what that means is that we're going to need to design that sort of line in 3-dimensional space. So let's just start going through it from the top as we normally would. And I said, let's eliminate y. All right, let's do that. I'm going to take equations 1 and 2 and rewrite them. X plus y plus z equals 8. That's equation 1. 2x minus y plus z equals 6. That's equation 2. We're going to add those together. 3x plus 2z equals 14. And we'll call that equation 4. And then we'll skip a line in our notes. And next, we're going to eliminate y again for sure, because we always eliminate the same variable twice. This time, I'm going to choose a different pair of equations. We used 1 and 2 before. Let's use 1 and 3, but I'm going to multiply equation 1 by 2, so that we have 2x plus 2y plus 2z equals 16. That's equation 1 times 2. I'm going to use equation 3 also, so that's negative 5x minus 2y minus 4z equals negative 30. That's equation 3. Let's add these together. And we get negative 3x minus 2z equals negative 14. That's equation 5. Now I'm going to use equations 4 and 5 as their own little system. We've eliminated the y variable twice, and I'm just going to copy and paste, I'm going to rewrite equation 4 under equation 5. And then I'm going to add them together, and what I get is 0 equals 0. That's how I know that there will be infinitely many solutions. Therefore, infinite solutions. Where are those infinitely many solutions? The way that we figure it out is I'm going to take equation 4 or equation 5, and I'm going to solve it for x. I don't know what word that was. Solve 4 or 5 for not z. I don't want to write out an equation that says z equals. Don't write out an equation that says z equals. Whichever other variable is there, solve for that one. In this case, it's x. So I will say that 3x is equal to negative 2z plus 14. That's equation 4. And then I'll divide both sides by 3. And I get x is equal to, I'm going to write it as negative 2/3 z plus 14 over 3. And I'm going to circle this because that's the x coordinate of my final answer. And then I have to figure out what the y coordinate of my final answer is. How am I supposed to figure that out? I'm going to take this x value, I'm going to plug it into any one of my 3 original equations, and then I'm going to solve for y. And what that's going to end us up with is an equation that just has, I'm going to plug it in for x, it's only going to have y's and z's in it. Sub into 1, 2, or 3, and solve, I don't know why I keep writing solve like that. Solve for not z, whatever the other variable is, solve for that one. Okay, let's plug this into equation 1. So my new x value is negative 2/3 z plus 14/3. And then in equation 1 it says plus y plus z equals 8. That's equation 1. Now we're going to solve this thing for y. I will add the negative 2/3 z over to the right hand side. So I'll put a little note on the right hand side that tells me what I did. I added 2/3 z to both sides. And now I'm still trying to solve for y. So I'm going to subtract z from both sides. That gives me 14/3 plus y equals negative z and a positive 8. And then we need to subtract 14/3 from both sides. That gives us y equals negative z. Now 8 is equal to 24/3. We're subtracting 14/3, so that leaves me with a positive 10/3 on the right-hand side. And I'm circling this because this is the y coordinate of my final answer. And with 4% battery left, I'm going to write down our solution to this system of 3 equations in 3 variables. The solution is an ordered triple, x comma y comma z, where the x coordinate is negative 2/3 z plus 14/3. The y coordinate of our solution is negative z plus 10/3. And the z coordinate is z. That's why I was asking you repeatedly to not solve for z in any of those previous instances, because I needed z to remain the independent variable. In order to generate some x and y coordinates of points that are on this line in three-dimensional space, you would select a z value and plug that into all three locations in our very unusual looking ordered triple solution. And you could calculate some actual coordinates in three-dimensional space of points that are on the line where all three planes intersect. This is a tough one, working with three equations in three variables. Use lots of paper. Keep skipping lines in between groups of work on the various combinations of those equations. Label your equations. Write yourself notes as you're going along. You only want to have to do each one of these problems once. So stay hyper-organized as you're going through. Take it slow. Double check your work as you're going along so that you only have to do each problem once. And by doing each problem once, I mean get every one of these problems right on the first attempt. It's going to save you time if you go slower from the outset and just get right answers every time. All right, off to it. Do some practice. Do well. Be patient. And I'll see you next time. Thanks so much.